So I think we can slowly start, and I really would like to start by welcoming both everybody here. Some faces, hi, good to see you. Yeah.
Hey.
People I've not seen for a while. Alex, you're still alive after Canada, so very good. Most of all, of course, I'd like to welcome our speaker, David Gershoni. As many of you know, David is spending, he's just won a Humboldt Prize to spend some time in Munich this year, and this is the first of what I hope are going to be a lot of productive visits. So he's been here for about a month now, and he's going to stay another till the end of July, so another kind of month and a half. David is a person that I think many of you who've been reading about quantum optics with quantum dots will know, certainly his work over the past 20 years. I think together with Gerhard, you guys were two of the pioneers of the field in terms of single dot spectroscopy and really kind of engaging quantum optics and bringing it together with semiconductor structures. So it's good that Gerhard, you could also make it here today. If you look at David's website, I don't want to embarrass you, but he has not just a long track record, but also he's a number of very prestigious prizes. David is from Technion, of course, as you know. He spent, I think, something like 10 years at Bell Labs back in the day with low dimensional, nearly 10 years, semiconductors.
If you integrate the time spent in the lab, it's more than
it's more than 10 years, yeah, in a time span less than 10 years. Apart from that, he's, of course, he has a number of prizes, fellow of the American Physical Society. You're also the the IPCS prize for quantum devices. So a number of prizes, and most of all, what I enjoy very much is that David is somebody who really wants to know how something works. So if you get into a discussion with him, he's always somebody who, let's say, will push you on the last point until you really find out what you don't understand yourself about your own experiments, which is a very good thing. So it's great to have you around, and I'm very happy that you can give this series of lectures. This is actually for the younger people, more of a general lecture to introduce David's activities recently. He's going to be giving some more focused lectures over the next few weeks. Those are advertised within Schottky Institute, but of course, MCQST members who are interested can also join these more focused lectures. Yeah, so I think I'll stop talking and I'll pass the word over to David. So welcome once again. And
thank you very much, John. It's a pleasure to be here. Not the first time, hopefully not the last time. It's always a pleasure to be here. Munich is a center of excellence that combines science and technology, and many things started here. And the level that the science is being and technology is being pursued here is always impresses me. So it's as I said, it's a pleasure to be here. And today it will be, as John said, I'm working many years on optical properties of semiconductors, and recent years specifically on semiconductor quantum dots. And it's a pleasure to be here together with Professor Abstreiter, who had a very fundamental contribution to these fields. Actually, I think the first observation of a single quantum dot was done here in his group by a paper from 1994, if I recall correctly. And in those days, nobody could have believed that a quantum dot will be, that what I will show you today, nobody dreamed about this, that this is possible. And I'm really happy that this long years effort of doing physics and technology on quantum dots provided us something which is unique. And I think it's actually, if we talk about quantum technology or quantum communication, this, what I will show you today, I strongly believe that this will lead to technologies that will enable in the future quantum communication. Okay. So, as you can see here, this work of mine is being supported very generously by ERC, by the Israeli Science Foundation, recently by the DEEP, German Deutsche-Israeli program, together with Professor Finley and Professor Sven Hofling from Würzburg and others. And I'm also grateful to the Alexander von Humboldt Stiftung for making able this. So very briefly, what I'm going to describe today is how we generate a device, a real device that can lead to a workable device that can produce entangled light. And it really produces single photons at gigahertz rates. And the single photons that we produce, each one of them is entangled to the photon before him and to the photon after him, and so on and so forth. I'll explain that. And currently, I think this way to produce entangled light, I think it is very, very important for future technology. We don't know exactly how, where it will be most but one of the examples is providing a quantum repeater. And a quantum repeater, when we want to make optical communication, you know that when we send light, so fibers, there is always losses. Okay? And in order to compensate for the losses, you need repeaters. So repeaters, just amplifiers, can repeat classical information. But to amplify quantum information, you need quantum repeater. And it is much, much more complicated. Okay? So one of the ways to do it is to generate entangled cluster states. And this is a description, schematic description of a group of photons. A photon is described here by this circle. And this connection describes entanglement. I'll talk about it later. Okay? And the idea that if we can generate this six-folded entangled cluster state or graph state, we can now use this cluster state to distribute entanglement. And one can, in principle, distribute entanglement by having two entangled photons. However, when, as I told you, when we use light, we have losses. And particularly today, when we do Bell measurement, okay, to sweep the entanglement, a Bell measurement is always probabilistic as of today. So the use of cluster state will enable us to compensate for this probabilistic nature of Bell measurement and for the losses. And we can do it without a memory, okay? Because the information then it will be embedded in the cluster state, and by local measurements, we will be able to translate to get back the information. So that's the useful thing about the things that we do right now, but I'm sure that it will be useful for many other things. So this is the description how such a cluster state can be used to communicate quantum information. We can divide this cluster state to 3 and 3, and by doing local measurement, we can repeat the measurement 3 times. If we have a much larger cluster state, we can repeat the measurement 10 times, 20 times, and using this repeatable measurement to compensate for the loss of photons. So this is just the most important application that I see today, that quantum dot or semiconductor devices, quantum devices have over any other technology that you can think of. And now I will try to convince you how we do that, to explain to you how we do that, and why it is going to be a viable device. So the outline of the talk will be as follows. I will first introduce you to the relevant theory. I will talk about confined spin qubits in semiconductor materials, and optical transition and selection rules. I will then describe this notion of the quantum knitting machine, how we produce one by one photon which is entangled with the previous photon and with the spin. This idea is also called machine gun, but I prefer knitting machine, simply because I'm coming from the Middle East. Okay, and now, and then I will talk about realization, how we do that. I explain to you how we demonstrate it, and how we do it with confined spin, and what kind of spin we use. I will then introduce you to the notion of indistinguishability. We produce a photon and another photon and another photon. The way to, since photons do not interact, the way to use photons is to interfere them. Okay? Bring two photons to a beam splitter. Okay, if they are the same, they will interfere, and you can use this interference to measure. Okay, but they should be exactly the same, and we measure the exactness of this being the same by a notion which is called indistinguishability. And it is, for technology, it is very, very important that the photons that we produce will be as much as possible indistinguishable, means the same waveform, the same polarization, the same wave number, whatever. This way they can interfere, and we can use interference to measure them. Otherwise, photons do not interact. Okay, and then I'll show you some experimental demonstration, and we will briefly, very briefly discuss possible future improvements that are really possible even today with the current technology. So let me start with the qubit. A qubit is a two-level system. I'm sure most of you know here, but one of my great teachers in the past told me that you should never take the pleasure of the audience to hear something that the audience already know. So I use his advice. So the two-level system is, we have actually only two levels, 1 and 0, and in physics they describe by two amplitudes, the amplitude of being in the state 0 and the amplitude of being in state 1. And since there are only two levels in the whole world, the probability, which is the amplitude square, the sum of them is 1, because we want to find the qubit. It is the state. It must be in one of the states. Okay. Now, physically, if you take this description of two complex amplitude and this condition, you can describe, if these are the eigenstates 0 and 1 here, any physical system you can describe as a point on the surface of this sphere, which is called Bloch zone. Okay. Now, if you prepare the system in a 0 state, this is an eigenstate, and it depends what is the lifetime of the state. It will decay. If you prepare it in the 1 state, it's the same thing. It will stay there as long as it can live, and nothing will happen. But if you prepare it in a coherent superposition, it's a plus superposition, which means 0 plus 1 with no phase between them. The phase is exactly 0. Okay, then if there is an energy difference between the 0 and 1, if you recall, for quantum physics, the eigenstate 0 develop in time with its energy, and the 1 develop in time with its energy. And as a result, because they are developing time separately, the phase between the two eigenstates will start to persist. Okay, you generate it here, but the phase changes on the equator, as you see here, and the mathematical description is shown here. Okay. And the precession rate will be exactly the energy difference divided by age. Okay, so if our qubit is not degenerate, then it precesses, and there is nothing you can do about it. Okay, so if you prepare a state here, it will also precess around this axis, which combines the two eigenstates. Okay, now let's talk about photons. So we know that photon light has polarization, and the general description of polarization, which comes out from Maxwell equation, if you want, is elliptical polarization. elliptical polarization means that the electric field that is combined with electromagnetic radiation, when the light progresses, the electric field will change its direction along this ellipse. Okay, so light propagates. It has propagation time, which is the wavelength divided by c, if you want. And during this precession time, it describes such an ellipse, the direction of the electric field. An ellipse, it can be described by two angles. One angle is the angle relative to the lab, and the other angle, this one, is just the ratio between the minor axis and the major axis of this ellipse. With two angles, what Poincaré told us many years ago, that you multiply these angles by 2, and then you can describe the polarization also on a Bloch's field, which was invented before Bloch. It's called the Poincaré's field. The polarization of light, just like the two-level system, spin, can be described as a point on the Poincaré's field. So now how we measure polarization? In order to measure the polarization, you have to describe this position, these two angles. And how do you describe it? You project it on 3 directions. And the projection, we usually choose bases. We choose the horizontal axis and the vertical axis. You have the diagonal axis and the anti-diagonal axis, and you have right-hand circular polarization and left-hand circular polarization. So you project the polarization on 6 bases if you want, and you measure the degree of polarization in the rectilinear base, HV, the intensity of the light in H direction minus the intensity in V direction, normalized by the sun, and you do the same for every other 2 bases. And since you have this condition that the intensity is the same, whatever base you use, means IH plus IV equal ID plus ID bar, and so on. So you need only 4 measurements in order to write the polarization. Okay? And the polarization is described by physicists using a density matrix. This is a density matrix written in the basis H and V, and you can see that there are 4 numbers that you need to know that. It can also describe mathematically in a more easier way to describe and to work, and I need it later on. We describe it by 4 real coefficients of the Pauli matrices. And the Pauli matrices, you remember, sigma x, sigma y, and sigma z, and we add another Pauli matrix, the identity matrix, sigma 0. And sigma 0 means that the light can be partially polarized. The degree of polarization sometimes is not really 1. It can be partially polarized, and the partial polarization is the coefficient of the identity matrix by this description, okay, of the density matrix. So we need 4 real numbers to describe polarization. These are the alpha mu. So a photon, a single photon, is a qubit. And since it flies easily from here to the sun and back, or to the moon, we call it a flying qubit. And a photon can transfer quantum information from one place to the other by the polarization, for example. There are other ways, but today I'll talk about polarization. Okay, so now that we know what a qubit is, I would like to give you an example for a single qubit gate, which is called the Hadamard gate. The Hadamard gate is defined very easily. You start from the input 0, you apply the Hadamard gate on it, and you produce the plus state, which is 0 plus 1, with 0 angle. The Hadamard gate, if you apply it on the 1 state, you produce the minus state, which is 0 minus 180 degrees between 0 and 1. And this can geometrically describe here as a pi half rotation. Okay? You start from 0, you produce the plus. If you recall on the equator, you start from 1, you produce the minus. So this is a pi half rotation, and I'll use it later on in my description. Now let me define example for a 2-qubit gate. So 2-qubit gate, we define in the most important one is the controlled, or most famous one is the controlled NAT gate. And we define one qubit as a control qubit and the other one is a target qubit. And the idea is that if the control qubit is 0, then the target qubit is not affected. But if the control qubit is 1, the target qubit reverses its states. So 0 and 0 goes to 0 and 0, 0 and 1 goes to 0 and 1, 1 and 0 goes to 1, 1, and 1 and 1 go to 1, 0. That's a CNOT gate. And now, if we have set of qubits on which on each qubit we can apply a universal 1-qubit operation, like Hadamard gate, but many others, and between each one of the qubits we can have a control NAT gate, then we can do quantum computing. Everything, this idea about the quantum computer will work out. That's all you need. But it's not easy to do, especially in order to do such a control NOT gate, you need interaction between the two qubits. One qubit should affect the other one. You need interaction. Photons, unfortunately, do not interact with each other, barely. Okay, and we cannot use this interaction to introduce 2-qubit gates. Okay? So, so what we do, the cluster says that I'll talk to you today, we will use the semiconductor, the spin in the semiconductor to introduce this guy. So before I do that, I just want to tell you about entanglement. So a 2-qubit gate may generate entanglement. And this is a simple example. If we define the control qubit as a plus state and we apply it on a 0 qubit, you do the arithmetic and you end up with this output state, 0, 0 plus 1, 1. You cannot describe this state in a separable way. You can only describe the 2 qubits together. And therefore, the notion for that is this is an entangled state. And in this case, the 0, 0 and the 1, 1 state have phase of 0 between them. It's exactly plus. Okay? This is very important. Okay? And this is an entangled state. And if we want to quantify the degree of entanglement, the way to do it is to measure the 2 qubits density state. And the 2 qubit density state is described by 4 measurements and 4 measurements on the other qubit together, all the variations. And as a result, we get a 4x4 density matrix, which describe the 2 qubit states. Okay, and this state that I describe here is called a maximally entangled state. And pictorially, you can see it this way. We have here 2 diagonal 0, 0 and 1, 1, and they are exactly half, and 2 anti-diagonal states, okay, a combination of this 0, 0 plus 1, 1 and this one, and which are also exactly half. So in order to measure the degree of entanglement between 2 qubits, we have to perform 16 measurements, and then we apply a mathematical trick, which was invented by one of my late teachers in the Technion, Professor Asher Perez the late. And this is, he defined this measure of a 2-qubit degree of entanglement as negativity. Okay? And the negativity is intuitively just the measurement of the size of the anti-diagonal terms. If the anti-diagonal terms are half, then the state is maximally entangled. If it's 0, they are not entangled at all. If it's in between, they are partially entangled. Okay, so that's the introduction about this quantum information. And now I'm turning back to the quantum dot or to semiconductors. Okay, how semiconductors are so helpful in producing this entangled state of many, many photons. So I describe here schematically what is a quantum dot. A quantum dot is a three-dimensional one type of semiconductor. In our case, it will be indium arsenide or indium gallium arsenide, and it is surrounded by another material. In our case, it's gallium arsenide. So the gallium arsenide band gap is described here, and the indium arsenide band gap is described here. Now the size is so small, so that the energy spectrum of carriers, of electrons and holes, this is the potential that they create for the electrons, and the size is so small that the spectrum is discretized. And here I describe in the conduction band, we have two electron states, and in the valence band, I have more. I describe here two confined states. Okay, and this is three-dimensional. So in each, they are fully discretized, and in each state we can find only two electronic states, one with spin up and one with spin down. That's the Pauli exclusion principle, if you want. Now, a semiconductor is called a semiconductor because at low temperatures, when the temperature is much lower than the difference between the valence band and conduction band, the valence band is full of electrons. All the possible states are full of electrons, while the conduction band are completely empty at low temperature. As we raise the temperature, some electrons go from the valence band to the conduction band, and the semiconductors start to be conductor because electrons can move and holes that creator can also move and transfer energy and the charge. Now, at low temperature, this quantum dot will be described as you see here. Before I excite this electron to the conduction band and start to talk about optical activity, I want to devote some description to these electrons in the valence. So happens that all the semiconductors, the valence band, is composed of p-like orbitals. The orbitals around the atom of the valence band, electrons are always like these eights. They have the generosity of 3. They can have 8 in z direction, 8 in x direction, and 8 in y direction. The 8 means that at the nuclei, the probability to find the electron is 0. But away from the nuclei, it increases. And this we describe with an orbital momentum of 1. That's how the valence band is composed in semiconductors. And I don't have time to exactly explain why, but that's a feature of all the semiconductors that are used that I know of. Okay? That's why they're semiconductors. Anyhow, in our case, due to the strain and confinement, what happens is that the electronic spin of the lowest energy electrons here must be parallel to the orbital spin. If they are anti-parallel, the spin-orbit interaction push the states much, much lower here, or higher in energy, relative kinetic energy. So we can neglect these states. So the electrons that we find here in the valence band must have total angular momentum projection, which is either plus 3/2 or minus 3/2, because they are the half spin is directed along the orbital spin of 1. Okay? So now we use light, and light can be polarized, as I said. For example, in this case, sigma minus mean left-hand circular polarization. So the light carry momentum of -1, if you want, in the direction of the excitation. Now this light comes here. It takes they spin up electron from the valence band and promote it to the conduction band. In the conduction band, the orbital momentum is 0. Electrons in the conduction band do not have orbital momentum around the nuclei. They make a Gaussian distribution around the nuclei, and their total angular momentum is 0. So what happened to the angular momentum of the electron we spin up that was here? 1, it was taken by the photon which was absorbed. Okay, the photon was -1, so it took a spin up electron from the valence band and brought it to the conduction. Okay, so but it cannot do it to this electron because the orbital momentum of this one is -1, and it cannot make it 0. You have to have right-hand circular polarization to do that. Okay, so the polarization of the light does not interact with the spin, but it selects the spin that we promote. Because of this fantastic feature of our quantum dot, that the spin and orbital momentum are parallel. Okay, so we select. We physicists defined. With time, I'm going too slow. It's okay. Okay, so we physicists define this missing, instead of talking about all the electrons but one missing, we define the missing one as a hole, okay? And hole has opposite charge and opposite and other quantum numbers. So if it was electron with spin 3/2, it's a hole with spin -3/2. So after the absorption, in our language, we describe electron with spin up in the conduction band, have total angular momentum with spin only, which is 1/2, and hole with -3/2. Together, -3/2 plus 1/2 is -1. Exactly the orbital momentum of the left-hand circular polarized photon that was absorbed. Now, this state lives for a while, and it decays radiatively. In our quantum dots, we measure it to be like 0.5 nanosecond, and I can explain, it's not a surprise, we can calculate it, and a photon will be emitted. And the photons that will be emitted will have exactly the energy difference between these two levels, and exactly the same polarization, sigma minus. We can do the opposite with right-hand circularly polarized photon, and when it recombines, it will give you sigma plus. And this, I think you can understand that with the polarization of the light, we can imprint the spin of the system. Because if we use sigma plus, we generate +1. If you use sigma minus, we generate an electron hole pair with -1. And if we use linear combination of the two, like edge polarization, we will generate a coherent superposition of the two spin states. And this we have shown in a pair in 2011. Okay, now spin qubits in a quantum dot. Okay. So when we generate such a quantum dot, there are ways to populate it either with electron alone, or with a hole alone, or with dark exciton, electron hole pair. After we excite the electron, we flip its spin, and now the electron hole spins are parallel, but the electron cannot decay because it should lose its spin in order to decay, because there is no empty space with the correct spin direction. And this we call dark exciton. Exciton is electron hole pair. Dark exciton is an exciton that cannot radiatively recombine. Okay, but it exists in a quantum. So these are the 3 long-lived spin qubits that we can have in a quantum. Okay, now let's call it lower qubit, because each one of them it's a 2-level system. The first one is the electron spin. The second one is a hole spin, 3/2 or -3/2, and the third one is a dark electron +2 or -2. And we can excite it optically. As I said, we add another electron hole pair by just using polarized light, as we wish. And this will take the electron spin qubit to upper qubit, which we call negative trion. It's electron hole pair in additional electron. And the two-level system here, since the two electrons are in a singlet set at 0 spin, the spin of the system, the two-level, is defined by the hole here. Okay, the excited hole here and here. It's a two-level system. It's an excited qubit. The same here. We can start with the hole, and then we will generate optically what we call positive trion. Is two holes in a singlet state, and the electron spin define the spin of the system, and it's a two-level, two-spin direction. And for the dark exciton, is you start from plus minus T2, and you end up with a bi-exciton, okay, which have two electron hole pairs. But if you can see here, the two holes here are in different levels. They cannot be in the same level. So one hole is excited here, and the two holes together, 3½ plus 3½ give you total spin of 3, and here you get total spin of -3. Okay, so 2 to 3, 3½ to half, and half to 3½ These are the lower energy qubit and the excited qubit. Okay, and then the decay combine better, optical back. Now, this system is optically connected to one another, and we call it an optical pi system. And why pi system? Let me explain very briefly. Let's assume that we have here the lower qubit state here. For example, in this case, the two lower qubit states, the exciton plus and -1, are connected optically to one state. This is called a lambda system, optically lambda system. Okay, by sigma plus, we will take this state to here. By sigma minus, we will take this state to here, but it's only one state. A pi system is the system that I described previously, in which the lower qubit, sigma, the -½ is connected to the -3½ by sigma minus optical direction, and this is connected to this one by sigma plus optical direction. It resembles pi in Greek, and therefore we call it pi system. And this is the optical system that we need in order to do this game of creating the cluster state. I will leave this aside for a second. This is a recent paper of us in which we use this combination between the lower qubit and the upper qubit in order to do full tomography of the spin. When I told you before how we do full tomography of the photon polarization, we put a polarizer and measure the photon polarization. To measure the polarization of a spin, it's a much more challenging way, and we developed recently a way to do it. We can measure and project and know exactly what is the polarization of the qubit before we excite it by making observable on the excited decay of the excited qubit. I don't want to, I will talk about it in our discussion later on. So we have a way to do full tomography of the spin in a semiconductor. Okay, I'll move quickly forward because I will need it, but now how one generate a cluster state of entangled photon. What's the idea? And the idea is due to Nathaniel Lindner, who's a professor in the Technion today. He was then a student in the Technion. He was actually the last student of Professor Asher Peres, the late, and Terry Rudolph. Terry Rudolph is a professor from Imperial College and now leading of PsiQuantum, a startup in the Silicon Valley, which is trying to do quantum computing based on photonic ideas, which are related to this idea. And we were able to demonstrate it for the first time 7 years later. Okay, so the idea is really relatively simple. If we can prepare the ground state of electron confined in the quantum dot in a coherent superposition. Suppose the phase here is minus between the spin up and spin down state. And we use resonance optical excitation to promote it to the excited level. Okay. And the excitation of the light is, for example, by H polarized light, which has both left and hand circular polarization, and it maintains, it's plus, it maintains the phase. So we translate the coherent superposition of the ground level to the coherent superposition of the excited level. Now the excited level decays by emitting a photon, and the photon carries with it polarization. Okay, and these polarizations that it carries, it's actually spin photon entanglement. Because let's see what is the wave function that we will get if we left this electron to process one period and return exactly back to the point where it was, or not process at all. You can see that the quantum state will be spin up with right-hand circular polarized photon minus spin down with left-hand circular polarized photon. So this is entangled state. We cannot describe the two qubits in a separate way. And the phase between the two combination is very well defined. This is an entangled spin photon state. Now, nothing prevents us from repeating this process again. Okay, and we repeat it again. And now we have 3 qubits entangled state, and again, and so on and so forth. So that's the idea. It's very, very simple. Okay, but it's difficult. It's not so easy, as you say. It took us seven years. There are many other people that are trying to do it. Recently, I've learned that the group of Professor Rampe here were able to do similar things using atomic ion as mediator between the photons. But the idea, the first idea, and the way we do it is with quantum dots. And this is, I believe, what will give us this technological advantage and ability to do. Okay, so now, so this way we generate the cluster state by repeating the process of here, entangling spin and photon by excitation and emission. That's generate 2 qubit gate, C node or C phase. And then we use 1 Hadamard gate. We let the precession complete only a quarter of a precession, and we repeat it again and again. Why a quarter? Because this way we generate an entangled state which is much more robust than the previous entangled state that I showed you. But in order to characterize this many qubit state, it's very difficult. In order to characterize entanglement between 2 qubits, we have to do 16 measurements, 2 in the power of 4. In order to characterize 10 photons, we have to do 2 to the 10 measurements, okay? And the density matrix that we will have will be 1,000 by 1,000, a million measurements if I want to characterize 10 photons. However, if I use this knitting machine, I don't have to do this measurement because I use the notion of induction, if you want, and let me explain that. Okay, what we do here, we repeat this step again and again and again. And in each step, we start with a spin. We start with a spin and excited, let it decay. That's entangling spin and photon. Use Hadamard gate, it's a single operation on the spin only, and repeat it again and again. Now, in each step, the photons that left the system doesn't affect the system anymore. What affects the system is this operation on the spin and the 2 qubit gate between the spin and the next photon. Okay, so all we need to do is to characterize this part. We call it process map. Okay, and what the process map does, it starts from a spin, which is described by a density matrix of 2 by 2, operates on it and give us spin and qubit, which are entangled. Spin and qubits that are entangled are described by a density matrix of 4 by 4, 16 elements. So how do we combine 4 to 16? We have to have 64 parameters. And there are real numbers that combine between the input and the output. And if we know that, we can describe the state. This is benchmark. By 64 parameters, I can describe the whole cluster state, quantum state. I don't have to do million measurement. I only have to know 64 measurement. Okay, that's what's called. So the 64 real parameters of this Hadamard gate and C-node gate is described here. Here you see the coefficient of the four Pauli matrices of the spin, and here you see the description of the 16 Pauli matrices of the spin and the polarization of the photon. So it's 4 by 16, and you see that we have 8 elements which are either half or minus half. This is the ideal case. In reality, things are unfortunately not as good, and what we measure is described here. Okay, this is it looks similar, but it is different. Okay, and what we call the fidelity with what we measure, and the ideal case was 82%. Okay, now why this is important? If we have an ideal process map, then if we measure the entanglement between distant qubits, the first one and the second one, or the first one and the third one, or the first one and the 10th one, the degree of entanglement will always be the same. Okay, that's ideal process map. It will be independent of the distance. But if the process map is not ideal, then the degree of entanglement between the qubits decay with the distance. Okay, and we can calculate this decay if we know the exact process, and we know. Okay. Now, how much time do I have? 10 minutes. Okay, so I'll rush. Now I described for you 3 qubits that we can use in the quantum dot. Which qubit we want to choose? Okay. So you can see here we prepare the spin qubit in a polarized way along the z direction, and we measured how much time it takes for the spin to depolarize. What is the dephasing time of the spin in the system? Okay, and this is the measurement for electrons, and this is the measurement for holes, and this is the measurement for dark excitons. And you can see here, actually, this measurement was first measured by the group of John Finley here. They were the first. The theory was from 2000, I think, but the first measurement was done in 2014, something like that, by the group of John Finley. And we repeated it. We just did the same things for electrons and for holes and for dark exciton in the same dot, because we know how to prepare the spin there. And you can see electrons dephase within 2 nanoseconds. And why is it dephase between 2 nanoseconds? Because the electron wave function have an antinode in the nuclei. And therefore, the interaction of the electron spin with the nuclear spin is very large. The hyperfine interaction is large for the electron. And therefore, it loses its spin to the nuclei much easier than the holes. The holes, remember, they have node in the nucleus, and therefore they dephase much slower. And you can see here that the electrons, the holes dephase in order of magnitude. This is a logarithmic state, logarithmic scale, and you can see that the hole dephases much slower and much less than the electron. So one would choose the hole or the dark exciton. And the first qubit that we choose was indeed the dark exciton. And why we did it? Why we choose the dark exciton? Because the dark exciton is coupled to the bright exciton, and we could use polarized optical pulse to initiate it in a coherent superposition, which we cannot do with Hall spin or electron spin. So we choose the dark exciton for that. And also the dark exciton is a total spin of 2, integer spin. And total spin of 2 does not have to be degenerate with a -2. And indeed, they are not degenerate. So even without external fields, it has natural precession. So we had the dark exciton and it naturally precesses. We don't need external field to do this. And that's why we choose the dark exciton. And we use the dark exciton as a spin to generate a cluster state. Okay, this was done in 2016, but the dark exciton has a problem. And the problem is exemplified here. It brings me to photon indistinguishability. Okay, how do we make sure that the 2 photons will be indistinguishable? This, or how we put them together at the same time on a beam split to interfere. So the problem can be described in the following system. We have the first, we generate a state, okay? We optically excite here this state. It relaxes to this place. And from here you have radiative recombination with a time we call T photon. And when it reaches to a final state, it also decays to the ground state with another time T final. So we have 3 times here. And one can approximate the indistinguishability by this 3 times. The indistinguishability is connected with the ratio between the tau photon and tau final, and the ratio between tau initial, the decay here, to the tau photon. Okay, and for the dark exciton, we excite this bi-exciton, then it decays to the excited dark exciton when the hole remains in an excited state. But the hole in excited state use photons to decay to the ground state within 100 picoseconds. Okay, so actually the lifetime of the de-excited dark exciton here is shorter than the optical transition. And when you put it into the formula, you end up with indistinguishability, okay, which is only 20%. And you would like to have indistinguishability of 1. Okay, so if we do it for the trion or for the heavy hole, as you can see here, we excite the trion to here. It's to an electronic state. The electron is excited, and the electron decays very, very fast because it's coupled to optical phonon, and which are resonant between the 2 electrons levels. So the electron decays within less than 20 picoseconds, and it becomes here, and then within 400 picoseconds, it decays to the ground hole state. But this is a ground hole state, and the lifetime is infinite. So you put the numbers, and you get indistinguishability of 95%. And the indistinguishability comes from here, the ratio of 20 picoseconds to 400 picoseconds. Okay? Because we do not resonantly excite as here. Here we resonantly excite. Okay? So how do we measure indistinguishability? You generate a photon by photon with a separation, let's say, of 2 nanoseconds. Okay? And you put here delay line, and you interfere them on a beam splitter. And you have 2 detectors, D2 and D1 here. And if the 2 photons are indistinguishable, they must go together either to D2 or to D1. And if we measure correlation between the 2 detectors, we will have no correlations if they are indistinguishable. Okay? So what we do here, we first of all produce here a lambda 2 plate, which makes the 2 polarization different. And if they are different, then the 2 photons are distinguishable. And therefore, we expect to see this blue curve that you see here. This is 0 time. This is time of the difference between the 2 photons, and this is twice the difference. And we can measure, of course, correlation between the first photon and the photons that comes 2 periods after, 1 period after, or before. But what is important is only, of course, this zero difference that we see here, that both photons arrive together. And you can see here that when it is polarized cross polarized, you see this is the area of what you get. And when it copolarized, you see here much less counts. And the ratio between the two is the measure of the indistinguishability. And indeed, for the dark exciton photon, we measure 17%. Okay? When we did the same for the heavy hole, this hole, you can see here that we measure 95%. Okay, you normalize, you take off the background, and that's what you get. 5% ratio here relative to this area here. Okay. Okay, so the previous quantum meeting machine, we excite the confined dark exciton. Okay, and the advantages were natural precession. We don't need magnetic field, and they can be initialized by a single optical pulse. The disadvantages, precession time cannot be controlled. It's given by nature, by the splitting between the +2 and -2 states. And the excited level final state is short-lived and therefore poor photon indistinguishability. Okay. Now we use the spin of a hole. Instead, we put B field in plane, and this we do in an excellent machine which was produced here in Munich by the group of by the company Atocube of Khaled Karaim. And this B field splits the two energies of the hole, the +3½ and -3½, what we call Zeeman splitting in a coherent superposition relative to the optical direction. But the field strengths we can control the precession time. Okay, and that's a big advantage. And also the photons are indistinguishable. Okay, so control precession, optimizing entanglement lengths. We talk about it, ground level final state, highly indistinguishable photons are produced this way. So the first work was published in 2016, and this is now, we put it on the archive last year, 2021. So now briefly, I describe what happens when you apply magnetic field. This is a 0 Tesla, I showed you the result. This is a 0.9 Tesla. This is the spectrum that we get. And when we go to 1 Tesla, this is the spectrum that you get. There are 4 splits due to this transition. The higher energy is H polarized between the excited state, spin up state, and the lowest energy state here. And the lowest state is here, H polarized. And there are 2 V polarized states, which are these cross states that you can see here. Okay. Now, of course, the indistinguishability is controlled, also reduced by the magnetic field. This is the average indistinguishability. And you can see that for it's becoming less because we separate the two photons energy. And when we go to ½ a Tesla, we see here clearly the quantum bits, which were observed the first time also here in Berlin in the group of Rempe in 2004. Okay. So how we work, I'm coming to the end of my talk. So it works the following way. We excite with the laser, H polarized laser pulse, this level, electronic recombination, electronic decay by phonons to this ground state of the trion, and then photon is emitted. The photon is being detected by one of these 6 detectors. Each detectors have LCVR, liquid crystal variable retarder, which controls the polarizations that we look at, and a polarizing beam splitter that take one photon, which is polarized, let's say H to D1, and the other one, the V to D2, and so on. We have 6 detectors that we use because the dead times of the detectors is 20 nanoseconds, and we excite less than 2 nanoseconds. Okay. And when we detect a photon, we detect its time and we know its polarization. And now we can do all these combinations that are needed to measure 64 parameters if you want to measure density matrix 16 by 16 and so on and so forth. Okay. So here, this is an example. The first photons that we detect, we can measure the degree of circular polarization of the second photon, as shown here. And from this, we can characterize what was the spin state before we excite. And we can also measure the polarization of this one, integrate it over time, and then do time resolved spectroscopy of the third photon. And from this, learn what is the spin state of this, of the spin before the second excitation or third excitation. Okay, so that's how we produce this measurement. And fortunately, I don't have much time, so I'll go much quicker now. This is the measurements that we produce from a single detector as a function of time and a function of magnetic field. And you can see here, we tune the re-excitation to be a quarter of a precession, and a quarter of a precession vary with the magnetic field. Okay, so at this is at 0.03 Tesla, very low. This is the separation, and 0.06, this is the separation, and at 0.09, okay, we were able, or we built our system in such a way that the precession time coincides with the repetition rate of our laser. So here, in this case, we generate actually an infinite strings of photons. The photons are produced again and again and again all the time. Here, it's only 3 photons. We wait, and another 3 photons, the same here. But here, they are generated infinitely, all the time. In my lab now, there is a laser that produces photons all the time, and each photon is entangled with the one before him and the one after him. This is a measurement in which we projected the first photon on Z direction and the second photon on the Z direction as a function of time. And here we projected the first one on Z direction, the second one on X direction, and the third one on the Z direction again. Okay, and we can measure the degree of polarization from this measurement, and we measured, for example, Z and then Y. Y is the projection of the spin. Okay, and for ideal cluster state, it should be 1. Okay, we measured Z and Z. For ideal cluster, it should be 0. We measure ZX spin Z, it should be 1, and ZXZ should be 1. Okay, and this is what we call witness or stabilizer. And measuring this alone is enough to demonstrate that we have a cluster state. Okay, and these are the results. And you can see here as a function of magnetic field. Okay, at this sweet point, we have a maximum in ZXZ. And this maximum can be translated to how many photons the entanglement lasts. Remember, the entanglement decay exponentially if the process map is not ideal. And here, the entanglement lasts for 10 photons. Okay, it means that the degree of polarization from photon to photon goes down by 10%, more or less. Okay, so and that's what we did. Okay, and that's a calculation. That's what we had in 2016 with the dark exciton. The degree, the exponential decay was 3 qubits, and now we have exponential decay, which is 10 qubits. Okay. Now let me summarize in this figure. This is a magnetic field, entanglement length. You see that at this sweet point of 0.09, we have entanglement length of about 10 photons. Okay, and these are the measurement, and this is the calculated one from the process maps that we measured only in this magnetic field of 0.12 Tesla. Now, why this is why we have a sweet point here? Why we have a maximum here? The idea is simple. What affects the robustness of the entanglement is the ratio between the decay time, optical decay time, 370 picosecond, and the precession time. Because the decay time is arbitrary. Okay, the photon can decay whenever it wants, but the precession is coherent. So if the arbitrary decay is not timed, this destroys the robustness of polarization. So the magnetic field let us make the precession time longer and longer. And the longer the precession time is, then the effect of the decay is reduced. Okay. Now, why can't we make it even longer? Because when the precession time becomes so long, remember the dephasing of the spin start to affect. Okay, remember the dephasing time was 25 nanosecond, and when the precession times become too long, okay, we have the reduction in the degree of polarization. Okay, this is our model, which is calculated from here. This is the process map that we measured. This is the indistinguishability, which in our current machine goes down to 80% here. It can be improved significantly. And this is the repetition rate. The stronger the magnetic field, the faster we produce photons. Okay, and here it was about 0.5 gigahertz. The precession, the generation of single photons is at a rate of 0.5 gigahertz. Every 2 nanoseconds we have a photon. Okay, this can be increased relatively easily if we use Purcell effect. Purcell effect reduces the radiative lifetime, and reduction of a factor of 10 was demonstrated in very many labs. And if you reduce the precession, if you reduce the radiative time by a factor of 10, you will increase the 10 to 50, where 50 photons, the decay of the entanglement will be within 50 photons. We will also have, we can also then make better the indistinguishability, because the indistinguishability is a function of the optical separation between the two Zeeman splitting relative to the radiative widths. If the Purcell effect increase the radiative widths by a factor of 10, this Zeeman splitting will be insignificant. Okay, so let me just conclude. We demonstrated on-demand generation of a cluster set of polarization and time indistinguishable photons at generation rates of gigahertz. As an entangling qubit, we now use a quantum dot confined heavy hole. Our quantum dot device produces very long strings of many photons with entanglement characteristic lengths of 10 photons. Okay, the generated cluster state is currently the best source of entangling photons that I know of. The Purcell effect can be used to significantly further improve both the indistinguishability and the entanglement robustness, and it's technically possible. One of the goals of the collaborations that I have with the group of Professor Finley here is to do exactly that. Current photon detection efficiency that we have in our lab is 1.5%. That means that we cannot do correlation for more than 4 photons. But this also, people have demonstrated now a single quantum dot single photon sources that are coupled to fibers with efficiency which is getting closer to 80–90%. Okay, you can read about these efforts of ours here, and the last work is in here, and also there are 2 papers that are needed to understand it better, which are also in the archive. One was published later. And let me just now thank all my collaborators, specifically Dan Kogan, who's the first author, Zuen Su, is a postdoc in my group, did much of the work, Oded Kenneth, who supported us with calculation and all the mathematics needed to calculate what the spin does in this mixed nuclear magnetic field and external magnetic field, and Ido Schwartz and Daniel Linder, which are not co-authors here, but supported us for all this development. I would like also to thank all the foundations that contributed to this work. And last but not least, please, thank you.